The first gas law we are going to look at relates pressure and volume, so P and V. And this is called Boyle's law. Look at the difference between these two containers. One has a volume of 4 liters. Notice it is a larger volume than this second one, which has a volume of 2 liters. So as our volume goes from 4 liters to 2 liters, look what happens to our pressure. Our pressure goes from 1 to 2. As volume decreases, pressure increases. We are going to look at the pressure-volume relationship and to be able to calculate an unknown pressure or volume when the temperature does not change. So Boyle's law says the pressure of a gas is inversely related to its volume when temperature and amount of gas is constant. If the pressure increases, the volume decreases, and we can say that the other way around as well. So as one increases, the other decreases. That is an inverse relationship. And if you think about it and look at this picture, the volume has decreased. So those gas molecules are more crowded, which causes the pressure to increase. Because they're more crowded, those particles are hitting the sides of the containers at a greater frequency, which increases the pressure. This indirect relationship can be written like this. P1V1 equals P2V2. This will show us the change of one to the other. Now let's use some easy numbers here. Let's say that my initial pressure was 3 atmospheres and I was in a container that was a 2-liter container. I just put in my pressure 1, my volume 1. Now let's say that my pressure changes, and when it does, my volume is decreased to 1 liter. So I had a container that was 2 liters, my container just decreased by half. Let's see what happens. Let's simplify the left side of the equation. 3 times 2 would be 6, and then I'm left with P2 times 1, and obviously to get P2 by itself I have to divide what it's attached to, so I'm going to divide both sides by 1. 6 divided by 1 is 6, so my P2 is 6 ATMs. Let's see what happened to that pressure. My volume decreased, going from 2 to 1. My pressure went from 3 to 6. So as my volume decreased, my pressure increased. If you don't like plugging in your numbers before solving for the equation, you can solve for whichever variable you would like first. Let's say we wanted to solve for V2. We could go, okay, to get V2 by itself, I need to divide both sides by P2. So we could say that V2 is equal to P1V1 over P2, and then you could plug in your data. Let's look at a sample problem. When Louisa had her asthma attack, she was given oxygen through a face mask. The gauge on the 12-liter tank of compressed oxygen read 3,800 millimeters of mercury. Here's what's important when you're going through a story problem. It's to label what are we given. 12 liters we need to be able to recognize as a volume, and because it was given to us initially, we're going to say it's our V1, and it said that in that 12-liter tank the pressure at that volume was 3,800 millimeters of mercury. How many liters, okay, so it's asking us to find V2 question mark, would the same gas occupy at a final pressure of 570 millimeters of mercury? So that's our P2. We're given an initial volume, an initial pressure, and a second pressure. We can find out what V2 is. Using P1V1 equals P2V2, let's plug in what we know. P1, we've got 3,800 millimeters of mercury. V1 is 12 liters. We need to find out what V2 is. So let's simplify what's on the left. 3,800 times 12 would give me 45,600. And then I brought down the 570 times V2. To get V2 by itself, I need to divide both sides by 570, and we should get 80. And I'm going to put a decimal point right there because that would be 2 significant figures. I've got 2 in that unit, 2 in that unit, 2 in that unit, so 80 point would be 1, 2. And let's see if that makes sense. My pressure went from 3,800 to 570, so the pressure decreased, which means our volume should increase. Our volume went from 12 liters to 80 liters, so it did Let's look at the link to health. During inhalation, the lungs expand. The pressure in the lungs decreases. So if the lungs are expanding, that means that the volume is increasing. And then the pressure is decreasing when that happens. Air flows toward the lower pressure in the lungs. During exhalation, the lung volume decreases. So volume decreases, therefore the pressure within the lungs increases. Air flows from the higher pressure in the lungs to the outside. Take a minute to look over this learning goal. All right, we have covered Boyle's law, pressure and volume. Now we're going to look at Charles's law, which relates temperature and volume. We're going to use that temperature-volume relationship to calculate the unknown temperature or volume when the pressure and the amount of gas does not change. Charles's law states that the volume of a gas is directly related to the temperature when there is no change in pressure and amount of gas. If the temperature, and our temperature needs to be in Kelvin, increases, then the volume also increases. So if it's a direct relationship, that means if the temperature increases, then the volume increases. And if the temperature decreases, the volume decreases. Let's look at the example right here. Here I have a volume of 1 liter and my temperature is 200 Kelvin. And we can see that we have a small flame here. Let's say that we make that flame a lot bigger and we heat it up. So we go from 200 Kelvin to 400 Kelvin. We can see that our volume went from 1 liter to 2 liters. Those particles start moving faster and with more energy, so it will push that plunger up because those particles are going to be hitting the containers more forcefully. We show this direct relationship with this equation. V1 over T1 equals V2 over T2. Now if that's a little bit confusing to look at this and see the fractions always messed me up, you can write this in a linear equation, but we have to do that bow tie method if you ever learned that in school. V1 over T1 equals V2 over T2. We would say that V2 times T1 is equal to V1 times T2. Let's write that down. V1 times T2 is equal to T1 times V2. Now it's set up in the same way that Boyle's law was set up, so I can take two variables and multiply them by each other, and then when I have my, let's say I'm trying to solve for V2, divide both sides by T1. I think you'll find that to be easier. Remember, the temperature needs to be in Kelvin. Let's do a sample problem. Helium gas is used to inflate the abdomen during laparoscopic surgery. A sample of helium gas has a volume of 5.4 liters, so that's our volume, and it has a temperature of 15 degrees Celsius. Let's do 15 plus 273 to get a temperature of 288 Kelvin. What is the final volume? So I'm going to say V2 question mark in liters. That's good because this is in liters. Of the gas after the temperature has been increased to 42 degrees Celsius. So that's our T2, but let's take that and add 273 as well. That'll give us 315 Kelvin. Now we just need to plug in all of the known variables. We have our equation that V1 over T1 equals V2 over T2. Let's plug in what we know. We know V1 is 5.40 liters over T1, which is 288 Kelvin, equals V2 as our question mark, and our T2 is 315 Kelvin. I'm going to go about solving this and making it a linear problem instead of fractions, so I'm going to cross multiply this and say that 288 times V2 is equal to, and then I'm going to multiply 315 times 5.40, and that gave me 1,701. And just like the last time, in order to solve for this variable, I need to divide by 288 on both sides. And that should give me a V2 of 5.9. Let's make sure that we label it correctly. Our volume initially was in liters, and so our final volume will be in liters. We wanted 2 sig figs because we've got 2 sig figs there, 2 sig figs there. This had 3, but 2 is our smaller number. And now let's see if it makes sense. We started with an initial volume of 5.4. My temperature is 15. The temperature went up to 42, so my temperature increased. Therefore, my volume should increase. We know that they're directly related. 5.4 up to 5.9, yep, that's an increase in volume. Take a minute to review the learning goal for Charles's Law.